Module 4 is proportions. We say a triplet of positive numbers, ABC, is proportional to another triplet, DEF, if the corresponding fractions are the same, which means A over D equals B over E, which equals C over F. For example, 2, 4, 9 is proportional to 6, 12, 27, because 2 over 6 equals 4 over 12, which equals 9 over 27. They're all 1/3. Note that the definition is symmetric, which means that it's also correct to say that 6, 12, 27 is proportional to 2, 4, 9. So when we check if two triplets are proportional, it's up to us which triplet we use as the first one and which one we use as the second triplet. It's important, however, to keep the numerators and denominators consistent, and all part of the same triplet, and written in the correct order of the triplets. Thus, even though 2, 4, 9 is proportional to 6, 12, 27, it would be wrong to intermix the number or the numbers or their orders. For instance, if we tried to say 2 over 6 equals 4 over 27 equals 12 over 9, we can see that the fractions are no longer equal to one another. This is because on the second fraction, the number 4 in the numerator, which was in the second place of the first triplet, got paired with 27, which was in the third place of the second triplet. That's what messed up the fractions. Another issue to watch for is that the numerators of the fractions also need to be consistent. In our example, we have 2, 4, and then 12, but 12 is from the second triplet, not the first. When we set up the fractions for these triplet, it's important to keep the numerators and denominators with the corresponding triplets written in the same order as the numbers that appear in our original triplets. Consider the triplets 1, 1, 4 and 2, 2, 5. They are not proportional. Let's check the corresponding between them. 1 over 2 equals 1 over 2 equals 4 over 5. Clearly the first two set of fractions are equal, but the last two are not. Thus we see that the two triplets are not proportional. An equivalent condition to have proportionality between ABC and DEF is to have a positive number, which we'll call K, such that D equals A times K, E equals B times K, and F equals C times K. For example, between the proportional triplets 2, 4, 9 and 6, 12, 27, if we let K equals 3, then we can check that 6 equals 2 times 3, 12 equals 4 times 3, and 27 equals 9 times 3. Sometimes this number K is called the proportionality constant. If ABC and DEF are proportional, we can use the notation ABC is proportional, which is noted by that squiggly line, to DEF. One last comment. If ABC is proportional to DEF, we can permute the order of the numbers that are written and still maintain proportionality. For example, if we swap the first two numbers in each triplet, we still have BAC is proportional to EDF, but it's important to be consistent and use the permutations by the same rule. If we swap the first two entries of the first triplet and the last two on the second triplet, we will lose proportionality between the triplets. Triangles of equal angles. If we have two triangles and they happen to have the same angles, then the corresponding sides to each angle form proportional triplets. In this picture, we have two triangles, and they all have the same corresponding angles. We labeled the vertices of the smaller triangle as ABC and the vertices of the larger triangle as A', B', C' in such a way that the angle at A is equal to the angle at A', etc. We can use the notation angle A to be the angle at the vertex A, angle B' to be the angle at the vertex B', etc. We can also use the notation AB to be the length of the line segment between vertex A and vertex B, and B', C' will likewise be the notation for the line segment between vertex B' and vertex C', etc. The segment opposite angle A is BC, the segment opposite angle B is AC, and the segment opposite angle C is AB. Similarly, the segment opposite A' is B', C'. The segment opposite angle B' is A', C', and the segment opposite angle C' is A', B'. Now we form the following triplets of numbers. side BC, side AB, and side AC, and side B prime C prime, side A prime B prime, and side A prime C prime. It's important that the order in which the segments are written in these triplets are the opposite segments of the corresponding equal angles between the two triangles. We can permute or change around the order of these segments, but it's important that they match up consistently according to the opposite angles that they correspond to. For example, it would be incorrect to write BC, AB, AC, and A prime B prime, B prime C prime, A prime C prime, because the first entry of the triplet side BC has the opposite angle, angle A, while the first entry in the second triplet, A prime B prime, has the opposite angle, angle C. This is not good because angle A is not the same as angle C prime. When we form these triplets, they need to correspond to the equal angles between the two triangles. Once we've written the triplets in the correct order, we have a proportion between the sides of the two triangles, given by sides BC, AB, AC, are similar or proportional to B prime C prime, A prime B prime, and A prime C prime. This translates to the following fractions. BC over B prime C prime equals AB over A prime B prime equals AC over A prime C prime. Let's illustrate an example using the concept of proportionality between sides of a triangle. Consider these two triangles that have the same angles. We wish to find the length of sides A and B. It's easy to get confused about how to set up the correct fractions, but if we match the opposite sides with the corresponding angles, it becomes much easier. The opposite sides of the 30-degree angle are 4 in the triangle on the left and A on the triangle on the right. The opposite sides of the 50-degree angle are B in the left triangle and 15 in the one on the right. The opposite sides of the 100-degree angle are 12 for the left triangle and 18 for the right triangle. With this, we form two triplets. 4, B, and 12 are proportional to A, 15, 18. Since they're proportional, we have 4 over A equals B over 15, which equals 12 over 18. The 12 over 18, for which we have both numbers, is going to be the key to solving this problem. So let's use that. Since 4 over A equals 12 over 18, we can cross-multiply those fractions to get 72 equals 12A, so A equals 6. As B over 15 also equals 12 over 18, cross-multiplying gives us 18B equals 180, and so B equals 10. Triangles formed by parallel lines. Let's have a triangle with vertices A, B, C, and we draw a parallel line from one of the sides of the triangle that cuts the triangle at points E and F, and produces a triangle within a triangle. The triangles ABC and EFC, let's say they have the same angles. To see why this is the case, let's focus on angles CEF and CAB as drawn in the picture. So since AB and EF are parallel line segments, the line that passes through points AEC, or BFC, is a transversal, as we discussed back in Module 1. Thus, it produces angles that are equal. CEF is equal to CAB. Similarly, CFE is equal to CBA. Finally, the top vertex angle, ACB, is a common angle to both the small triangle, EFC, and the big triangle, ABC. Now that we know that both of these triangles have the same angles, we can set up proportional triplets. Thus, CE, CF, EF are proportional to CA, CB, AB. It follows from here that CE divided by CA equals CF divided by CB, and also they both equal EF divided by AB.